Welcome back to The Explainer. It's finally here, guys, the sixth and final part of our six-part series diving into the Merg-E language specifications. Today, we're officially crossing the bridge. We're moving out of the version 0.3 testing environment and stepping right into the highly opinionated strict version 0.4 language extensions. Now, if you've been with us for the first 5 parts, you know this entire domain-specific language is built on a very strict least authority philosophy. Today, we are looking at how that exact philosophy scales up to handle heavy mathematics and runtime fault tolerance.
For our agenda today, we're capping off our journey by looking at parts 20 through 23 of the spec, dimensional type systems, deprecating standard floats, tensors and matrix literals, and finally, flow control and exceptions.
Okay, let's just dive right into it. Section 1, Dimensional Type Systems.
So, Part 20 introduces us to the underlying academic theory, the actual mechanics of compile-time dimensional analysis. To really grasp how Merg-E tracks physical units, we have to start with this definition of a dimensional type system. Basically, by using abelian groups over integers, this system achieves complete dimensional inference, and it does it in polynomial time. To put that simply, the compiler uses a math system of integer vectors, tracking exponents for things like length, time, or mass, to guarantee your computations are physically consistent before the code even runs. It's kind of like a giant, flawless puzzle. Now, what's super interesting here is the contrast between standard early erasure methods and the DTS methodology. In languages like F#, dimensional units are checked for errors, and then, well, they're just discarded right before the actual execution code is generated. Merg-E does the exact opposite. It preserves that critical dimensional data as metadata, carrying it all the way through the multi-stage lowering process.
And because that metadata is preserved, we get this amazing unbroken chain of causal effect properties. Each compilation step literally consumes the output of the step right before it. Step 1 figures out the dimensional range, right? Which then directly informs Step 2, selecting the exact hardware representation. And that dictates Step 3, your memory footprint and allocation strategy. It seamlessly weaves physical logic directly into deterministic memory management.
Moving right along to Section 2, Deprecating Standard Floats.
So this is where those academic principles become extremely strict rules in Part 22, and it forces a huge shift in programming habits. Merg-E makes the objective, highly opinionated choice to prioritize absolute dimensional type safety over the flexibility you'd normally expect from traditional floating point numbers. It simply deprecates your standard float and complex types. Instead, you are required to use R quantity and C quantity types.
If you want to use floating point numbers in version 0.4, the language physically enforces compile-time dimensional analysis by requiring SI or Planck units. By tossing out standard floats, the compiler can jointly resolve numeric representation and memory management without any ambiguity. You literally have to specify what your numbers represent in the physical real world.
Let's jump to Section 3, Tensors and Matrix Literals. As outlined in Part 21, we are pivoting. We're moving from singular physical quantities up to massive, complex structures. Merg-E now natively supports pure numeric n-dimensional matrices across all 7 of its numeric type families. While earlier specs leaned heavily on directed acyclic graphs and data frames, Part 21 finally gives the language the heavy lifting muscle it needs for intensive structural computations.
Tensors seamlessly merge those strict physical quantities we just talked about with matrix math specifically tailored for cryptographic workloads. Remember, Merg-E is built from the ground up for Web 3.0 bots and Layer 2 nodes, so this approach guarantees that the intense compile-time type safety translates perfectly into the complex data arrays needed for crypto processing.
All right, last but not least, Section 4, Flow Control and Exceptions.
For Part 23, we shift our focus from compile time to runtime behavior. What actually happens when things go wrong? Take the number 1024. This number marks the start of a rigidly claimed block from user error 1024 to 2047, and that is the only range developers can alias for custom exceptions. In Merg-E, you absolutely cannot just arbitrarily define whatever error code you feel like.
Staying true to that core least authority architecture, the language forces you to explicitly consume a resource to claim one of these error types. Why? To avoid system-wide collisions. When you consume a resource to claim an alias, the compiler makes absolutely sure that if an error is thrown across different actors or network membranes, its meaning is globally unambiguous.
But what happens when an error goes unhandled?
Well, if an unhandled exception occurs in an asynchronous, non-inline invocation that isn't bound to a blocker, it follows one uncompromising rule: fire and forget. The invoker doesn't wait for a response, and it certainly doesn't fail just because the child process failed.
This means Merg-E completely abandons the standard programming paradigm of bubbling exceptions up the stack. In a traditional language, an error cascades up and crashes your whole application, right? Not here. This DSL strictly limits ambient failure to maintain total system integrity. If an actor crashes, that failure is isolated entirely to that one specific actor.
So as we officially close out this 6-part explainer series, I want you to consider the unique trade-offs required to build a framework like this. Does the benefit of hyperspecific dimensional type safety and strict least authority isolation actually outweigh the loss of general-purpose programming flexibility? It's a fascinating question, and one you'll have to answer based on your own specific engineering needs. Thank you so much for joining me throughout this entire series, and as always, keep looking for the structure beneath the code.